All right. So this question right here, the top question says, um, draw the substitution products for reactions A and B. And it also says for reaction A, explain why the rate of reaction will not be affected when you increase the concentration of the nucleophile when the reaction is done in ethanol. Explain why the rate decreases when the solvent is switched to DMSO from ethanol in reaction B. All right, so let's do that right quick. So the product is going to be the same no matter what. So what does this product look like? This substitution product. So we need to figure out what's the substrate, what's the nucleophile, and where the reaction is going to take place, and what the product is. So which one of these two between between here and here, which one do you think is the nucleophile?
The one on the right.
This one. Good. Excellent. Right? That can be written, excuse me, like this. Right, and that's a pretty good clue as to which one is going to be the nucleophile. If you have a metal, non-metal combination like a salt like that, that's a pretty good clue as to which one is going to be the nucleophile. All right, so if that's the nucleophile, by default, this is my substrate. And then this group right here, which is what we call a tosylate, is my leaving group. And if you look on the leaving group list, let me show you where that is on that list. It is right here. Toluene sulfonate. So it's shortened down to tosylate. And you can see the pKa of the conjugate acid is -0.6. So that means it's a pretty good leaving group. All right. So we all that information we already know how to find all that. Right now, we just need to figure out what the product is. So what is the product of this reaction going to be? It's a substitution. And so if it's a substitution, what is the general outcome of that?
The nucleophile just replaces the leaving group.
Nucleophile replaces the leaving group. That's it. So I can write this like, not like that. Like that, boom, and then here. And then my sodium is going to end up with the leaving group. Right, your leaving group generally, if it's neutral, when it leaves, is going to be negative, and it'll generally form a salt with whatever your counter ion is for your nucleophile. All right. So the question, let's go ahead and do the bottom one too. So this is, you can see that the cyanide has a negative charge. So that's by default, that's going to be my nucleophile. It's actually a pair of electrons on carbon and on nitrogen. And then this is my substrate. And then, this is my leaving group. It's called a triflate. Go to the list, you'll see it right here. Change the color right quick. All right, this is triflate, it's OTF, trifluoro methane sulfonate. All right, and So let's go back to here. And well, let me take that back. That triflate leaving group this is trifluoroacetate. The triflate leaving group is not on here. But the pKa for the triflate looks like this. Let me correct that. Triflate looks like this. It does have a CF3 on it. That's where the trif part comes from, the trifluoro, but it actually looks like this. Right, so this is OTF, trifluoromethane sulfonate. This is actually trifluoroacetate. So that's a different leaving group. But the triflate has a pKa, the conjugate acid has a pKa of, I think, negative 13.5. All right. So that's an excellent leaving group. That's the point I'm trying to make. All right. So when we go back to here, what's the product? Because we know the products if we won't know anything else at this point. Because all it is substitution of the leaving group with the nucleophile. All right. So that product is going to look like this. Make sure I got enough carbons. All right, let's go back and answer the questions now. First question says, for reaction A, explain why the rate will not be affected when you increase the concentration of the nucleophile when the reaction is done in ethanol. Right, that's the key to the question right there. So you have two solvents. DMSO, what class of solvent? Go ahead, Tia.
Oh, wait, can you repeat? You repeat the question?
Can you hear you say that again?
Can you repeat the question that you said?
It says explain why the rate of reaction will not be affected when you increase the concentration of the nucleophile when the reaction is done in ethanol.
Is it because the nucleophile it doesn't affect the rate, like it's not in the rate law or something?
Okay, so that's good. So what mechanism, if I'm doing this in ethanol, is ethanol protic or aprotic?
It's protic.
Protic, good. So if I have a protic solvent and an allylic substrate, because this is allylic, right? And it's secondary. That's pointing to, and you're right, you're absolutely right about what you just said. It's pointing to the fact that the mechanism is SN1 in a protic solvent. So that means that if in ethanol, the rate law, what would the rate law be?
Would it be rate equals K times the substrate in the base?
Only the substrate.
Okay.
There's no base, right? It's a substitution.
Okay.
So it's just the rate equals K times the concentration of the substrate only. So what you say is right. The nucleophile is not involved in the rate law, and the reason is because the reaction is SN1. So this is an example of one of those substrates that can be either or. It can be SN2 or SN1 depending on the other factors. And so the solvent in this case is going to facilitate SN1. And then up top is DMSO protic or aprotic?
Aprotic.
Aprotic. So that would indicate that if we switch solvents, that would indicate that the mechanism will more than likely switch to SN2. Right. So the answer to the question, explain why the rate of reaction will not be affected when you increase the concentration of the nucleophile when the reaction is done in ethanol, and ethanol is going through an SN1 mechanism. So the rate law doesn't include the nucleophile. So there's no nucleophile included. Let me fix that. Come on, Russell. No nucleophile included. All right. And this question is specifically designed to go through all the factors that affect the mechanism and determine whether something is going to be SN2 or SN1. All right. Let's do the next question. Question C, because we've drawn the products for A and B. Question C says, explain. Let me change colors of my highlighter. Explain why the rate decreases. Note the term decreases when the solvent is switched from DMSO to ethanol in reaction B. So that's this reaction right here. Why do you think that? Let me move this too, because I don't want you to think that product. I want you to think that product that I wrote was for DMSO. So why do you think that? Look at the reaction. Tell me whether you think that's going to be SN1 or SN2. That's the point of that question.
It's the SN2.
Yes, why you say that? You're right.
Because it's on a primary carbon, the leaving group.
Come on, child. That's right. So it's a primary substrate. Primary substrates only do SN2. They do not do SN1. Right? So the mechanism for this particular reaction is going to be SN2 only because of that primary carbon. All right, so now let's answer the question. If I switch solvents from DMSO, which is what? We just said it up top, that DMSO is a product, and then ethanol is product. What did we say what happened to a SN2, a reaction that's going through an SN2 mechanism if you do use a product solvent? What does that product solvent do?
What solvenate with the leaving group?
It will solvate the nucleophile, not the leaving group, because in this case, remember this is concerted.
Okay.
So the leaving group is leaving at the same time the nucleophile is coming in. All right. So if I switched over to a product solvent, it's going to slow the reaction down because it's going to actually solvate that cyanide anion.
Oh.
And that's bad, right? Because I showed you that how that would look on an energy diagram, where when you solvate the nucleophile and lower its energy, you make it less reactive. Right, so that one question, it basically covers like almost all the factors that determine whether or not a reaction is SN2 or SN1, and some of the reactions that increase or decrease the rate. What would the rate law be for this reaction, since we know it's SN2?
Would it be the rate equals K times the substrate and then the nucleophile?
Yes, excellent. So rate for in this case equals K times the concentration of the substrate, and then times the concentration of the nucleophile. Right, so both substrate and nucleophile are involved in the rate, and that's because it's a second order reaction, and it is bimolecular. All right. All right, let's go down to the next question, unless there are questions about that. All right, let's go to the next question. All right, and let me say this too, when you submit this page and whatever we do, none of it should be blank, as we're going through it right now and taking time for questions and whatever. So, because I noticed like on the last homework, like how do you turn in a blank sheet when we're doing the work in class? Unless you ain't in class. You might be watching Maury or something, but like when we turn this in, these questions that we're working on now in class should be answered. At minimum, they should be, at least those should be answered. All right. Let's go to the next one. What mechanistic pathway would you expect the following reactions to follow? So look at these two reactions. And this is where I know I sent you a video with this ICE method: identify, characterize, and execute. Right. So identify means looking at the substrate and the solvent and the nucleophile, and then characterizing means it's either protic or aprotic. It's a good nucleophile or bad nucleophile. It's primary, secondary, tertiary substrate. And then execute is just looking now and saying, okay, I know these things are all favor SN2 or SN1 or so on and so forth. So if we look at 1 and 2, what type of substrates are those? The answer to that question is wherever my leaving group is, right? I look at the the environment of the leaving group. Is it secondary? Is it primary? Is it allylic? Is it tertiary? So what are these? Both of these are the same. They just have different leaving groups. But what do you think? Is that what type of substrate is that?
Secondary.
It's a secondary substrate. Good. So we know if it's secondary that it can do either SN2 or SN1. So we got to look at something else now. This is a pretty decent nucleophile, right? What about the solvent? Is acetone protic or aprotic?
Protic.
Let's go to the list. What is it? Right here. Polar aprotic solvents. Acetone is aprotic. Ethyl acetate, acetonitrile. And when you see these written, like ethyl acetate, you might see that written like this, or acetonitrile would be written like this. And then of course DMF, dichloromethane. And what I don't know why I don't have DMSO on here, but DMSO is also polar aprotic, and that looks like this. All right. So all of these are aprotic. So acetone is aprotic. So let's go back to our example. This is aprotic. Now we can make a better decision because we know if it's protic and it's a secondary carbon, then it's probably going to do SN1 and not SN2, right? So what do you think? Protic solvent, secondary substrate, good nucleophile, and look at the product. What do you notice in the product compared to the start material?
Does it have inverted stereochemistry?
It's inverted. So that's a clue, right?
Mm-hmm.
Which of the two substitution mechanisms proceed with inversion of stereochemistry?
SN2.
SN2. So we know all of these things point to the fact that this is a SN2 mechanism. Right? All of it, the different factors, when you add them all up, you see that it's a SN2 mechanism. All right. So let's go to the next question. So based on your answer to the question 1, what's the correct rate law? So if you predicted that it's SN2, what should the rate law be? Just in a generic sense.
Would it
Would
be,
it be D?
yeah, D?
Yes. That ROAC is just an abbreviation for the substrate. Right? It's not B because the acetone, the solvent is not involved in the rate and not involved in the rate law, although the wrong solvent can slow the rate down. And then it's not here because the nucleophile is not just by itself, right? We said it's SN2. That means it's bimolecular, so it can't be either one of these. So it has to be D, right? You have to account for and what D, but that two-term rate law tells us a bunch of stuff. It tells us that it's bimolecular, that it's concerted, right? And that it is a second order overall. All of that we can glean from that, just that rate equation. All right, let's keep pushing with this. Are there any questions about that part? All right, let's keep pushing then. I'm gonna keep that visible. It says if the concentration of sodium methyl sulfide is decreased by 10 times, what happens to the rate? All right, let's look at the rate law. And let me write this out in maybe more practical terms so you can see it.
Would it be F?
You said F?
Yeah.
Okay, think about what you just said. So F is saying that it's going to increase 20 times if I decrease the concentration of one of my components 10 times. That's not feasible.
Okay.
In order for it to be F, I will have to increase one of those by 20.
Okay.
Right? Because what the rate law looks like here is here, right?
Okay.
Right. So one of them is 1, that's unchanged. And the other one is 1/10. So it's basically like me dividing the whole thing by 10 if I decrease the concentration of one of them by 10, right? So it will have to be H. And let me give you an example of that. So if I let's say for the rate law, let's say I double them both. What happens to the rate? This is a product, right?
They increase by 4.
Yes. What if I triple them both? Right? And this is a product. We just multiply them together. We're 9 times increase. Right? If I took one and halved it and left one constant, right? Then the rate should decrease by what? Mm-hmm. Right. So that's how that works. Like whatever I do to one term or the other, it's going to affect the rate. So if I take one term and divide it by 10 and leave the other one untouched, it's going to cause the whole rate to be basically decreased by 10. Right, because it's bimolecular. So whatever if I change one or the other, it's going to affect the overall rate. All right. Questions about that? All right. Let's go to the next question then. It says reaction of R2-methyl-3-bromobutylbenzene. That's the start material right here. With sodium methoxide, that's my nucleophile. Gives 2 products, Choose the best representation of the transition state from the list below. How do we know what the transition state is going to look like? What do we need to know first?
Whether it's stepwise or concerted.
You need to know, thank you. That's excellent. We need to know whether it's stepwise or concerted. If it's stepwise, then the leaving group leaves first before the nucleophile attacks. So that's going to have a totally different transition state than if the nucleophile is attacking at the same time the leaving group is leaving, right? So let's push that a little further. If it's stepwise or concerted, which of the two substitute, because obviously this is a substitution, because you can see the ethoxide here has replaced your bromine leaving group. So you know it's a substitution. But what type? Is it SN2 or SN1? Once you answer that question, the rest of it becomes academic after that. What do you think?
SN2.
Why do you say that?
Because the solvent is a product.
You know, ethanol, anytime you see a solvent with a hydrogen on it like that, alcohol, it's protic. All alcohols are protic. Let's go back to the list. So these are all your protic solvents right here. Acids, alcohols like methanol, ethanol, isopropanol, water, and then non-carboxylic acids like sulfuric acid, phosphoric acid, so on and so forth. So anything that can give up a proton is considered a protic solvent. So ethanol is protic, which is going to determine, along with one other piece of evidence, what type of substitution this is. So we got protic solvent, we have a secondary substrate, and we also have, rather than inversion, we have racemization. Right? What that means is that you get both stereoisomers instead of just getting the inversion where you only get the opposite stereoisomer. Anytime you see racemization, that's a signal that it's a SN1 mechanism. Can somebody tell me why it racemizes if you watch that video on SN1? What's the first step in the mechanism if it's SN1?
Also leaving group.
Loss of leaving group. Which makes this a carbocation, is that right?
Yeah.
Which is actually, in essence, an empty p orbital. All right, so this is my intermediate, and then my nucleophile can attack from either side of that empty p orbital. It can come here, or it can come here. All right, either side of that p orbital can be attacked, and that's why you see racemization. Right, so because of that free attack on either side, either lobe of that p orbital, that's what leads to racemic products. Right, so that's a dead giveaway that is SM1. So you said the loss of leaving group is the first step. That's good. All right, So now, now let's go look at these transition states. If that's the first step, the loss of the leaving group. All right. Which one of those is and we know it's SN1, right? So the rate determining step is the loss of leaving group. Which one of those is the right transition state? Which one of those is indicative of a leaving group leaving from the substrate? Right. Well, first let's go and let's ask this question. Which ones can we rule out?
TS3 and TS4.
You want to rule those out? Are you sure about that? If the first step doesn't involve a nucleophile, then wouldn't transition state 2 and 1 be ruled out?
Yeah.
Oh, I thought we were doing it for the whole thing. Okay.
Yeah, no, we're gonna rule. So I was asking which ones can we rule out, so we can rule these two out, right? Because those are not; these are both bimolecular, right? But we just said that this was a SN1 mechanism, so we know it's unimolecular, so we can rule those two out right away. Does that make sense?
Yes, sir. I got you.
All right. Now we can look at TS3 and 4, because both of those are indicative of, you see a partially broken bond between the leaving group and the carbon in the substrate. But which one is the correct one though?
TS3.
3. Good. Why do you say that? I agree with you.
Because it has that that was called, but the carbon has a partially positive charge.
Yes. And the leaving group has a partially negative charge. What's wrong with TS4? Like basically, what's the difference between those two? That's going to be the problem.
It's the leaving group has a partially positive charge, the negative.
Yeah, and that's not right, right? Because the leaving group is leaving with 3, well, actually 4 lone pairs, because that bond that's breaking is heterolytic and is polarized in this direction. So that charge shouldn't be partially positive. Right, so that has the wrong charge on it. So it's TS3, which has the proper charges, and it excludes the nucleophile, which is not involved in that rate determining step, loss of leaving group. So all these factors help us to see that this is a SN1. The scrambled up stereochemistry is a dead giveaway. Anytime you see that, you can, and it's a substitution reaction, you can put all your money up in Vegas. That is SN1. When you see that scrambled stereochemistry like that, it's really rare to see an SN2 reaction with racemization. Very rare. All right. All right, let's go. Any questions? All right. If not, let's go to the next set of questions. Let's go to answer these first. Actually, let's run through 8.61. It says predict. Now look at what it's asking. This is the key to any chemistry class is to find out what the question is asking for. Sometimes we don't read the question or we don't interpret it properly and we just start doing stuff. All it's asking you to do is to predict the major product for each of the following E2 reactions. So it's telling you that it's E2. So we know it's an elimination. We know when it's E2, we need to find what? The leaving group and the alpha protons. That's the key to figuring out the E2 mechanism, at least figuring out the product. Even if you don't know the arrows, you should be able to figure out, okay, this is my leaving group, and these protons are the ones that get pulled off by the base, right? So when it says E2, this is what I know for a fact. I know that there's a base involved. I know that it's second order. I know the rate law is K times the substrate times the base concentration. Right, these are all things I know. And I know that my products are going to be based on wherever that leaving group is and wherever the alpha protons are that are adjacent to it. So in that first example, let me zoom in on that. Where's my leaving group?
Bromine.
Bromine. This is my leaving group. Right? What does that mean for the alpha protons? Where are they?
To directly adjacent.
So on this carbon right here,
And then the one on the left.
I'm gonna just write them in. All right, those are my alpha protons. And it says the major product. When it says major for an elimination, what does that mean?
And it's gonna happen majority of the time.
Yeah, okay, that's true. But when we think about elimination, what are we making in an elimination reaction?
The pi bond.
Making a pi bond. So based on this is based on Zaitseev's rule. It's based on Zaitseev's rule, which says that which pi bond is going to predominate?
One that's most substituted.
The more substituted pi bond is going to be a major product. Good. All right. So the more substituted pi bond is going to be your major product. So for this substrate, I'm just going to write out the two products so we can get a feel for this problem. And then we're going to go through and do the other ones. Notice my base is sodium hydroxide. And then for these two products, I'm going to have this as one of them. And then my other product is going to look like this. Notice where the double bonds are, here and here. Are y'all following that? So one of those double bonds is going to come from here. That elimination, and the other one is going to come from that elimination on that side. Right, so those will be my two products. So which one is major? Which one is more substituted?
The one with the 3 hydrogens.
The one, you mean this one right here?
Oh, yes, sir.
All right, so let's look at the substitution on it. It's got 2 hydrogens here, 1 hydrogen here, and 1 carbon right here. The one up top has 2 hydrogens and 2 carbons. So it's actually the top one that's the most substituted. This the one that's at the bottom, the terminal alkene, is the least substituted. Because the substituents we're talking about are carbons. Right, so this is going to be major up top. Are you following that?
Yes, sir.
All right. So that top alkene is going to be major and the bottom one is going to be minor, because the top one is disubstituted and the bottom one is mono substituted. It only has 1 carbon attached. All right, let's do, we got 5 minutes. We can get through a couple more of these. Let's do the bottom. Let's do B. Actually, B is really simple. Well, yeah, let's do B. So where's my leaving group in B?
Bromine.
Bromine. Sodium hydroxide is my base. Right? we know it's the E2. So all we're really looking for is the leaving group and the alpha positions, right? So here we got an alpha hydrogen here, and we got one here. That's going to give me two products because my leaving group is between two carbons, right? So what's the first product going to look like? Where's the double bond going to be?
Would it be between the third and fourth carbon?
So it's going to be wherever the alpha protons are, right? So those two carbons here, that's going to be one site where the elimination takes place. And then the other site is going to be on the other side where the other alpha carbon is. So when I get, and that's how you can predict the products even before you even draw them out, you can predict them. So we can write those out. I'm gonna draw this one first. Like that, that's one. And then the other one is gonna be here, like that. Hope I got enough, I think I got enough carbons. All right, so let's look at the substitution pattern. So the bottom one has a carbon here and a carbon here. The top one has 3 carbons attached to it. So which one is more substituted? Top one. So this is major. And this is minor. Right? Any questions about that? Y'all are eerily quiet on this Friday. When I was first started teaching here, I didn't realize that the reason people were quiet on Fridays was because of like whatever it was, Thirsty Thursday. Everybody going out partying and come in Friday hungover. But now I don't know if Thirsty Thursday still exists. Hopefully it doesn't, but yeah, y'all are super quiet today. That's okay. Let's do the next. Actually, let's not do C. You can do C on your own because it's just like A. The only difference is the carbon chain is shorter and it's a different base. This base right here is, you'll see it written as KO T-bu. Sometimes you'll see it written out like this. It's a very good base. This is negative, and then potassium positive, potassium terpetoxide. All right, let's do D. Where are my alpha protons and where's my leaving group?
Leaving group is bromine, and you have 3 alpha carbons on the left and then 1 on the right.
Yep. Somebody draw that. Go ahead, Tia, since you already unmuted. Can you draw the 2 products in that we'll get? This is the last example we'll do. We'll pick up on Monday. Okay, good. 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 Excellent. Which one is going to be major?
The bottom one.
The one at the bottom, because it's more substituted. I don't know if I can't see it on my screen. No, wrong. So that's 1. That's what an alkene is. So it has 1, 2, 3, 3 carbons attached. That should be over some. So here, this carbon and the other carbon right there. So that alkene has 3 carbons attached to it. I didn't realize I could do that. Well, I tell you, the Lord works in mysterious ways. And then the top carbon only has the It's mono substituted. It only has one carbon. So the bottom is major. And then the top one is minor. All right. We got to stop here. It's 9:51. Monday, we're going to pick up on, keep going through this. I sent you a bunch of stuff to like look at the other day. If you haven't watched all of it, or at least read the section in the chapter, if the videos are not helping, then you at least got to read the chapter or read something. Google, pull it up on Google, do something, but don't come cold. All right. We'll pick up on Monday. Probably finish this up between Monday and Wednesday, and then we'll be on to conjugation after that. All right, so we're gonna pick this up on Monday, and y'all have a good weekend, and I'll see you then.
Have a good day.
All right, y'all take care.
All right, thank you.
All right.